When you think about chemistry, it's easy to picture a bunch of random stuff bubbling away in beakers. But what if I told you it's actually more like a carefully choreographed dance? The thing is, chemical reactions aren't chaos at all. They follow really specific steps, almost like dance moves. So let's learn those moves. So, can chemicals actually dance? Well, in a way, yeah, you bet they can. And once you learn the basic steps, you can start predicting what's going to happen on the chemical dance floor pretty much every time. It's kind of like having a chemistry superpower. And this picture really nails the basic idea. Just like dancing, a lot of chemical reactions are all about elements swapping partners. But it's not a free-for-all. There are rules, Who leads, who follows, and who's allowed to switch. And that's exactly what we're going to get into. Okay, let's kick things off with our first dance move, the single displacement. The easiest way to think about this one is like the classic cut-in you see in old movies, where someone new and confident steps right onto the floor and steals a partner away. So here's the more official breakdown. In a single displacement reaction, you have one lone dancer, we'll call it A, and it walks up to a couple, B, C. Now, if A has more, let's call it dance floor cred, or in chemistry terms, if it's more reactive, it literally cuts in, kicks B out, and forms a brand new couple, AC. Poor B is just left standing there all by itself. And that brings us to the most important question of all. Who actually gets to cut in? Because not just any element can barge in and displace another one. Nope. There are some very strict rules on this dance floor. And these are our rule books. For metals, we use something called the activity series. You can just think of it as a reactivity leaderboard. The elements at the very top, like lithium, they're the kings of the dance floor. They can cut in on anyone below them. For nonmetals, we look at the periodic table. Their reactivity increases as you go up and to the right, which makes fluorine the most popular dance partner out there. All right, let's put these rules to the test. Let's say we have our lone dancer, aluminum, and it's approaching the couple, nickel bromide. Is anything going to happen? Let's find out. So we just follow the steps. First, we spot our lone element, aluminum, which is a metal. That means we go check our rule book, the activity series. We look it up and, yep, aluminum is higher on the list than nickel. Ding, ding, ding. That means it's more reactive, and the cut-in is a go. Aluminum displaces nickel, hooks up with bromide, and nickel gets kicked to the curb. So the reaction definitely happens. But here's where it gets really interesting. What happens when the rules aren't met? Say we try to react copper with hydrochloric acid. We go to the activity series, and we find that copper is actually below hydrogen on the list. That means it's less reactive. It just doesn't have the juice to cut in. And the result? Absolutely nothing. No reaction. The original couple just keeps on dancing. Okay, on to our next dance. This one has a lot less drama than the cut-in. It's much more organized, more elegant. We call it double displacement. It's basically where two couples meet up on the dance floor and just neatly trade partners. So in a double displacement reaction, we start with two couples, AB and CD. The positive ions, that's usually the metals, A and C, they just switch places. So A ends up with D and C ends up with B. And just like that, you've got two totally new compounds. It's a really clean, simple swap. You can see it right here. The two positive ions, the yellow A and the green C, they're the ones making a move. See how in the final products, they've just traded partners. A is now with D, and C is hanging out with B. It's just a really balanced, elegant exchange where nobody gets left out. All right, let's see this partner swap in action. We're going to react sodium sulfide with hydrochloric acid. Right away, you see two compounds, so you should be thinking, aha, partner swap. Okay, first up, we identify the positive ions that are going to do the swapping. That's sodium and hydrogen. We still check our activity series, and, well, sodium is way more reactive than hydrogen, so this reaction is for sure going to happen. Sodium partners up with chlorine to make sodium chloride, that's just table salt, and hydrogen pairs with sulfur to make hydrogen sulfide. We just balance it out, and there's our final equation. All right, time for our grand finale. We're going to switch up the tempo completely. We're leaving this structured ballroom and heading straight for a high-energy, fiery mosh pit, the combustion reaction. To put it simply, combustion just means to burn. It's what happens when a substance, usually something like a hydrocarbon fuel, reacts super fast with oxygen. Honestly, this isn't really a dance. It's more like a wild chemical party that gives off a ton of heat and light. Think about the engine in your car or the flame on a gas stove. That's combustion. Now, not all these chemical parties are created equal. If you have plenty of oxygen, you get a nice, clean burn. We call that complete combustion. The only things you produce are carbon dioxide and water. But if you start running low on oxygen, the party gets messy. That's incomplete combustion, and it creates some nasty stuff, like toxic carbon monoxide and soot. So there you have it. You've learned the basic dance moves: the cut-in, the partner swap, and the fiery finale. Now let's pull it all together so you can step onto the floor and be a confident reaction predictor yourself. So here's your quick cheat sheet. If you see a single lone element reacting with a compound, you're almost certainly looking at a single displacement. If you see two compounds reacting with each other, it's probably a double displacement. It's that simple to get started. Okay, pop quiz time. Let's test your new skills. Take a look at this equation. We've got potassium, K, reacting with aluminum chloride, AlCl3. What kind of dance move is this one? Take a look at the dancers. What do you think? Yes, you got it. It's a single displacement. We have that lone element, potassium, walking up to a compound. And just so you know, since potassium is way higher on the activity series than aluminum, it is definitely going to cut in. Awesome. Let's do one more. This time, we have sodium chloride reacting with sulfuric acid. So, two distinct couples on the dance floor. What's the pattern here? Exactly. That's a classic double displacement. We have two compounds at the start, so we know they're about to do that elegant partner swap. Sodium will go with sulfate, and hydrogen will pair up with chloride. Perfect. So there you have it. You've learned the fundamental steps to chemistry's big dance. You can spot the patterns, you can predict the moves. But this is really just the beginning. There are so many other incredible reactions, so many other dances happening all around us, all the time. The only question is, what chemical dances will you discover next?